Okay, I'm going to go over some of the constructions that we have on the material that I sent. We're going to do a perpendicular to a line through a point on that line. So you got a line, you got a point on the line. You want to create a perpendicular to this point, to this line through that point. So you take your compass, put it on the point, inscribe a couple of marks on each side, like that. Then open it up a little bit. I'm going to draw an arc like that on that side, and then on that side. So where these 2 points connect, they'll connect through that point in the center, and by definition this is perpendicular, like that. So in this case the point was in the middle of the line, and that's good. If you had the case where the line is like this and you got a point here, you want to do a perpendicular to a point on the end of the line, you have to extend the line so that you can do just what you did up there. Similarly, so we'll mark the 2 points on the line like that and like that. Okay, and then open it up a bit, maybe a half distance between the 2 points, and draw the arcs like that and like that, and again draw through the 2 points, and you've got a perpendicular like that. So now if you had an angle, let's say we had this angle here that we drew up earlier, and we didn't have all these extraneous marks, but we wanted to see if this was a right angle. How would you measure that? So I drew a right angle here, at least it appears to be. If you want to see if that is really a right angle, what you'll do is you'll have to extend the line out, do just basically what you did before. Through that point here, and draw a right angle in the same way you did before. Increase that out, do that, like that. Draw a line through those 2 points, and in this case it doesn't look like it's exactly a right angle. So if you have any kind of spread like that between what you drew and the line you're trying to measure, then it's not. I think the example in the test, there are right angles, and they should line up perfectly, but that's how you tell. Okay, now we want to drop a perpendicular from a line that's not, from a point that's not on the line to the line. It's very basically the same kind of thing that we did before with the point on the line. So let's start on the point. We'll draw a couple of arcs intersecting the line there and there. It doesn't have to line up with any of these points, it just happened to work out that way. Then you come down, put your point there, make it a little bit smaller, but not more than halfway. So, and then you draw an arc like that on that side, and an arc like that on that side, and then draw your line through that point. And voila, you have a right angle. Okay, now if we want to draw a line that's parallel to AB through P, what you're going to do is recreate this angle here, up here. So the way you copy an angle, if you remember, you can either, there's two ways to do this. You can copy the angle, or you can create a perpendicular to this point here, so that anything that's perpendicular to this line is also perpendicular here. So by definition, if this is perpendicular to this and this is perpendicular to this, then these two lines will be parallel. Okay, so let's do that. So this time we have a point on the line, and we're going to create a perpendicular to a point on that line. Same thing we did before. Got to widen it out a little bit. I think about halfway down makes a good arc. And like that. And so if you draw a line through that and that, then you'll have another line, and these two lines here, this one and this one, are parallel. That's the symbol for parallel. I don't know if you can read that or not. Okay, isosceles triangle. There's several different kinds of triangle. There's an equilateral triangle, which has 3 equal sides. Isosceles has 2 equal sides, and the third side that is not equal. So you'll be asked to draw an isosceles triangle with this as one of the sides. So you've got one side, but you want to have 2 other sides that are, if they're the same size as this, then it's equilateral. But we're told that we want an isosceles, so isosceles only has 2. So we're going to create 2 lines of the same length, so we're going to use our compass to measure. So it doesn't matter. I think that's probably as good as any. So we do that on one side, and we do that through the other, and that's kind of a squashed isosceles triangle, but it's isosceles nonetheless. So there, and like that. So that's one isosceles triangle. Now you can create a bunch of other isosceles triangles doing it the same way. Let's make one that has the 2 other sides that are longer than the base. So we'll just extend this out like that. I'm going to draw it on the bottom. So we're going to do this down here. If you can see that, probably not. Way down there, yeah, okay. And I'll do it on that side as well. So now we have more of a skinny isosceles triangle, and it looks like that. Okay, you've been asked to draw a rectangle with sides congruent to these 2 lines. Okay, congruent means they're the same length. So a rectangle has 2 sets of equal sides, and it also has, every angle in the rectangle is a right angle. So we can draw, let's start with the base. So we'll draw us a line down here, and we'll measure CD first with a compass. Okay, I'll make a mark on this bottom line, and we're going to create a side that's congruent with CD, and that's what that is. So, but now we need to create perpendicular to this point, because we're going to drop AB down on that, a line that is that same length. So going back to our construction of a perpendicular line to a line on a point on a line, we do that first, if you remember. And then we'll take the compass on both sides, open it up a little bit, about there, draw an arc on both sides, like that. Now we have created a perpendicular through this point, if all goes well. So we can draw that line. I'm going to put it up top. So we know that this one has to be AB, so let's measure the length of AB with our compass. Did that right there. Mark that and mark that. So at this point we could say, let's create another perpendicular here and then draw it over there. But all you've got to do is draw an arc that's this length here and an arc that's this length over here, and where they intersect we'll make a triangle, so I mean a rectangle. So let's do that. Now I've already got this measured, so I'm going to put this over here. So I measured this distance here over here. Okay. Now I'm going to measure from here over here that distance, which will give us our two parallel sides of a rectangle, which is a parallelogram with right angles. So we're creating parallel lines here and there. So now we have our rectangle with, it's a parallelogram with right angles, which is a rectangle. And now we've constructed, and we only really had to construct one right angle. These are right angles as well, because of the way we did it. Now we're going to talk about the concept of a tangent. Tangents are used with circles, and a tangent is defined as a line that touches one point on the circle. And I'll show what I mean by that. That's not clear. So you have a circle, with the center right there. So if I want to create a tangent, I have to draw from, I'm just going to show you this. So we've drawn, this is the diameter going through the center. So a tangent would be a line that goes through a point, but it has to be perpendicular. So we have to create a line that has a perpendicular to this point. So how do we do that? Well, we've done it many times already, so let's do it again. So extend the line out so we can see it. Create a perpendicular to a point on a line, the line being the line that goes through the center of the circle. So just do everything we've done before and open this up a little bit, like that, like that. I've seen a lot of students that like to just draw part of the thing like that. And try to come up with a perpendicular from that point down, but the problem with that is you're kind of guessing when you get down here, so you have to have the other side to it. So you draw a line from there to there, then this line here is a tangent. It's a tangent to the circle because it touches at one point and one point only, and it's perpendicular to a line that runs to the center of the circle. Okay, let's say that you want to do a circle that's tangent to a line, okay? And you want it to be tangent at a given point. Say, we'll call that point T for tangent. So, by definition, the tangent touches the circle at a 90-degree angle from a line that goes to the center of the circle. So if we draw a perpendicular line through this point, then we can draw circles all up and down this line that will pass through this tangent. I'll show you what I mean. So let's do our perpendicular again. We do a lot of this in geometry. Like those perpendicular lines. Another one there. And there. So, now we have a perpendicular through a point, and we can draw any number of circles. Let's say we want one that's got a radius of that. Then we can do that. Right? We draw a circle. So basically, any point on this line, you can adjust your compass to that length that goes through that tangent point, and that will also be tangent to that circle. So there's really an infinite number of these circles that we could draw, bigger or smaller. They can be many different sizes. So anything along this line can be the center of a circle that has a tangent to that point. So we like to put circles around things and inside of things. So when you put a circle around something, it's called circumscribing. When you're putting, it's like circumnavigating the earth, you're going around the earth. Circumscribing a circle about something, you're drawing a circle around it. But it's just not just any circle, but like a triangle, you have to be able to have all 3 points of the triangle touch the circle. I'm going to show you how to do that. So we're going to circumscribe a circle around the triangle. Let me draw that. So we have a circle, a triangle rather, that has 3 vertices. These points here, here, and here are called vertices. So we want to draw a circle that touches each one of those 3 points. In fact, any 3 points that are not collinear, that is, they don't align on one line, can describe one and only one circle. There's only one circle that will go through those 3 points. And I'm going to show you how to do that with this. So what we're going to do first, since hold on, you know that pesky perpendicular bisector? We're going to make one on one of these sides here. So let's do that on that side and do another one on this side. And I'm going to do it on this one as well. You really only need to do 2 of them, and you'll figure out why in a minute. You don't really need to do all 3. So now we have 2 perpendicular bisectors of the 2 sides, like that and like that, and they cross at a specific place. So what we will find out is that magically, for some reason, if you adjust the compass to the points, it turns out that all 3 points will now magically be circumscribed through the points. I mean, it's not exact because I was not real careful about where I put the point, but you can see it goes through all 3 points. So that's how you circumscribe a circle around a triangle. Now, putting a circle inside of a triangle is different. So outside of a triangle, you use the perpendicular bisectors of two lines. If you do a third line, it'll go through the same point. So that's why you only really need to do two of them. So if you want to inscribe, which means you draw a circle inside, you got to be able to find the center of this triangle such that the circle will touch and be tangent to all three sides. So with this inscribing a circle, instead of bisecting the sides, we're going to bisect the angles. So remember that bisecting an angle is very similar to bisecting a line. So you do that first, and then you can use the same radius if you want to. It works. There and there. So the angular bisector goes from there through that point. Looks like that. So the angles here and here are the same. So now we're going to do the same thing up here. You could do it either on one side or the other. Let's do it on this side. Looks like it's a little bit easier to get to. So we draw our angle, our arc. We draw that and that. Another angle bisector. I think I slipped a little bit there. Be kind of careful with these constructions. So where these two, this one and this one cross, is another center. And it turns out that if you put your compass there, that you should be able to draw a circle through that point. And if I had done it correctly, it would have been tangent. It wasn't exactly accurate, but you got a tangent here, here, and you should have one here as well. It would be if I were a little bit more careful about the way I did it, but you get the point. Okay, we talked about circles and tangents and stuff like that, so we're going to draw a circle first. One circle. And if we want to, say we want to draw a circle, another circle, that's tangent to this point here. Remember we said that you could draw an infinite number of circles with a center along this line here that would have a tangent there. So if we do it inside, you could do that. Not a problem. We just do that and adjust the compass to that point, and it's by definition a circle that's tangent to the same point. You can also do it outside the circle, so let's do it outside and adjust the compass there. So we're going to have another circle that is tangent to that same point. So the point is that there's an infinite number of these circles you could draw, big, small, whatever, bigger or tiny, whatever. So that's circles tangent to a circle. Okay, you're going to be asked to draw a circle inside of a rhombus. A rhombus is a parallelogram that has equal sides, but they don't have right angles, so it's like a square that's been pushed over. So I'm going to draw essentially a 2-inch rhombus. 2 inches here. And we can complete the rhombus by measuring 2 inches here and going up there and there. So this is a perfect rhombus. It's got equal sides. The one that you have may not be perfect, but it kind of looks like it is, so we'll go with it. You're not going to be able to inscribe a circle inside of this that touches all sides. You would have to draw an ellipse. So we want to find the center of this guy, so there's several different ways we can do it. Probably the best way to do it is to bisect the two angles. Now we don't need a compass to do this because we all got to do. Okay, we lost that. Looks like it's not going to let me put the light on, but I think we have enough light you can see what we're doing. So if we put the compass there, we find the shortest distance, it looks like we can do something approximating a circle inside. So it looks like it should touch here and here and here and here. If I've done it correctly, it should work fine. Inscribe means put a circle inside. So we've got a regular pentagon here, 5 sides. It has to be regular. If it's not a regular pentagon, this won't work. So should be able to do a perpendicular bisector of a couple of the sides like that, and let's do it this one. Since it's regular, it'll all go to the same location. So you're basically trying to find the center of the pentagon, and this works fine. Okay, so this should be the center of the pentagon, and we should be able to draw tangents at all those points if it's a regular pentagon, and it appears to be, so it should work fine. So it did. So now we have done pretty much everything, except we haven't done a regular hexagon, which is a hexagon that has 6 sides and they're all the same length. So I'll show you how to do that. Turns out that a hexagon inside of a circle is basically a series of equilateral triangles. So at 60 degrees, like that. So we're going to measure the radius. If we do the radius, of course, it won't work, right? Because the radius well, it does work actually. So we're going to create the triangles are equilateral, so they all have the same length. So it's going to be the length of the radius, so that'll work. I was thinking that pi is 3.14, and it's not an equal number, but since we're not doing arc lengths, we're just going lengths of sides. We should be able to do that, and then do another one, the same radius there, and then we draw like that. So if we connect all these vertices like this, then we end up with a hexagon inside of a circle. This is easy. A pentagon inside of a circle is a pain. It's there's a lot of work involved in doing that, but this is simple, so you should be able to do this. Like that. But it has to be regular. And we've done lines parallel to a given point through a given point. That's okay. The next thing is probably the hardest thing, and I'll show you how to do that. It's not intuitively obvious, so because we know that we can't trisect an angle or arbitrarily divide an angle up into many different parts, but you can do it with lines, and it's kind of a cool trick. So let's say we have a line from A to B, and we want to divide it up into 5 spots. So 4 spots is easy, 4 lengths is easy because you bisect it and bisect it again, that'll give you 4. But 5, how do you do that? Well, we're going to, okay, so back to where we were. Sorry it dropped out there. So we're measuring this arc length, and we're going to mark it off on all the points. Okay, now we have our parallel lines. We can drop. You can see that they're parallel. 1, 2, 3, and 4. So now we have 4 segments, 1, 2, or 5 rather, 3, 4, 5, and these are all the same distance because they're parallel. And so now you divided this segment up into 5 segments, 1, 2, 3, 4, 5. So that's kind of cool. You can't do that with an angle, but you can do it with a line.